Hello. How are you doing? I hope you are fine after yesterday's party, but if you still need to recover, I brought you some chocolate bars from Switzerland, so Swiss chocolate. If you wanna, you can grab it, because they're limited, so don't hesitate to take them. Today I'm going to talk about how we completely rewrote our static code analyzer for Kotlin. So it would be more about static analysis for Kotlin, less about how we actually rewriting things, but I hope you'll have some fun. And before we start with the topic, let me introduce myself. My name is Marharyta. I'm software engineer at Sonar. I'm frequent conference speaker. Also, in my previous life, was a conference organizer. Maybe some of you will see me at previous Kotlin Conf, or maybe visited our meetups. My native city, Kyiv, and I'm a big fan of programming languages like Java, Kotlin, Scala, TypeScript, and so on. And of course, Kotlin is my favorite one. And this is my Twitter handle. Sometimes I tweet some engineering stuff. Sometimes I tweet about life. So if you want, you can follow me. And usually when I introduce myself, I say, there is one more important thing you should know about me. And before previous year, it was always that I do boxing, so be careful when asking tricky questions. But these days, it's something different. You know, I'm Ukrainian. I was born and raised in Kyiv, and I live in Geneva only 2.5 years. And you know, my country is now in danger. We have a problem with our neighbors, and we have to fight for our freedom. And thanks a lot, all of you who actually support Ukraine, who stand with Ukraine. And if you want to support, there is a QR code leading to some foundation, a charity foundation that helps Ukrainians to survive under attacks. So thanks a lot. Let's proceed. What we are going to talk about today. Today, actually, I'll talk a little bit about the history. What was the reason why we actually needed to rewrite our static code analyzer for Kotlin? Why actually we needed something else? Then I'll talk a little bit about Sonar Kotlin 2.0. So it's actually the brand new analyzer that we rewrote. Then we'll talk a little bit about the user feedback that we received, achievements, and a few takeaways that I hope you'll take from these presentations. This is how you can see some report in the Sonar 8.9, which was a previous LTS, where you can have the old version of Kotlin Analyzer. So you see there are 64 bugs on some average project, no vulnerabilities, so security is safe, and technical debt is around 4 days. And then, if we take exactly the same project, without no changes, but analyze it with the latest version of SonarCube, which is the current LTS, you see the number of bugs is 3 times higher. There are 200 vulnerabilities, and you will remember there were 0 before. And the technical debt is a month, while it was 4 days. So does it mean that my job is to make your code worse? Actually, it's not about your code. It's about the analyzer that's starting to detect more. So what happened? In order to understand what happened, let's go back to the history and forward to the past. History. How static analysis in general work. I don't know how you're familiar with the concept, but let me introduce it. Let's imagine you have some source code, for example, some simple hello world with some function. What we are doing? We are transforming it into abstract syntax tree. And today I'll talk a lot about syntax tree. I don't want you to remember all the structures, so let's think a little bit abstractly, and let's just see the tree there. And our analyzers, we are taking this tree, running some rules, some checks, some features, and transform it into the result. So we show you here you have some vulnerability, here you have some code smell. This one is just info for you. And this is just an example. So in simple words, the scheme looks like this. Source code, tree, and result. Where is the problem? The problem is that every tree for every language looks differently, because syntax is differently and abstract syntax tree is different. In Sonar, there was an idea that maybe we can have one tree that rules them all. So let's have some universal tree that can cover all the languages, so we write rules only once, and then they're immediately available in all the languages. Like 2 years or 3 years ago, idea sounds like nice idea, let's implement it. So how we implemented it? We actually had nice abstract tree, which is very concrete for ideal for example, Kotlin or Java language, and we transformed it into a sort of more of a sketch tree, like with missing some parts, but it could be universal for many languages. And then we run all the checks on that tree and generate a result for you. Thankfully, fortunately, this approach was working only for a couple of languages, like Kotlin, Scala, Go, and Ruby. So for like flagship languages like Java, C#, C++, we still had their own analyzers, and they were not touched. But what was the problem with Slang? Let's firstly discuss like pros and cons, and then we'll talk about the problems. First of all, you write one rule, and then it's available in many languages. Like we wrote one rule, and then it's present in Scala, Kotlin, Go, and Ruby. Great. Then, if you want to add a new language, for example, if tomorrow we decide to support Rust, we just need to write a converter to this our Slang tree, and then that's it. Immediately, and out of the box, we have like 40 rules. And that's it about the pros. Let's talk about cons. Maintenance. Sometimes language evolves, features are added, so we have to update the syntax tree for the concrete language. Sometimes this change affects our universal tree. And the change in the universal tree sometimes affects all other trees. So for example, change in Scala language can affect change, like we have to change some support of Kotlin, Go, Ruby, and other languages, and it became a nightmare to maintain. Then rules precision. Because we cut some branches, the precision was pretty low. And for example, in Kotlin, we had to cut object, we had to cut extension functions, so it was pretty dumb, stupid analyzer. Language-specific rules, because of lower precision, we are also losing the opportunity to implement rules for language-specific features. Testing is harder, because now you have to test like 5 times for every rule. And another problem, there was no semantic information in this. So all the rules that we wrote were just about the syntax. And I don't know if you're familiar or know with semantic, but let me, in simple words, explain you what it is. So semantic model. We talked a little bit about like source code into tree and analyzer result. And what is semantic in all this scheme? Let's imagine that you have 2 files. One file is just class, hello world with some function, and another file contains another function that uses this class hello world and uses another function. Without semantic, they're just completely different for us, and we have no understanding that this hello world is actually that hello world. But with semantic model, we can understand that this hello world reference is actually that hello world class, and this x.f function is actually a function that is defined in hello world class. So with semantic, we can understand the context behind the tree, the relations between other trees, and relations between different nodes of these trees, and a lot of more information, but that's just in simple words. So semantic is very important to write high precision rules, and we were missing it. So this is actually the why. Why we needed to do something with Kotlin. First of all, because Kotlin is growing their popularity, and you see, definitely see this at this conference. There are a lot of people here, a lot of talks, and all the frameworks, all big companies are supporting Kotlin, so that would be dumb not to see the growth of the language. Then user feedback. Because our company and our analyzers, we try to be closer to the community, and of course we try to listen to our community, and we saw a lot of people demanding proper support of Kotlin. Another point that we like Kotlin, and we wanted to use the language in our code base, But we could not because we don't have a proper static analysis and we cannot write correct code, so we need some static analysis tool, at least for us. And from another perspective, we have people who like managers and company objectives, and we were thinking that maybe it would be nice also to conquer the market of security and Android, and of course we have to support Kotlin properly. And Slang, our current approach, was limited. We had to do something with this, we had to think it, because we needed a proper support of Kotlin. That's it about the why. That was the time to release Sonar Kotlin to the 0. So, how we did it? That's what we had. You remember the scheme. We had source code, transformed it into abstract syntax tree, then transformed it into universal tree, generated result. What we wanted? We wanted source code into the abstract syntax tree of Kotlin without nothing intermediate, immediately to result. But, of course, we had some legacy. Of course, we already had some existing rules, and we needed to live somehow with it, so that's what we implemented. Looks scary, a little bit ugly. When we implemented this, we knew that this is not actually the final result. This is not how we wanted to proceed. So we marked the Slang part as a technical debt, promised ourselves that we'll eventually get rid of it, and once we released to the 0, we actually got rid of it. So we fulfilled our promise. Now there is no Slang part in Kotlin Analyzer. Yeah. So Kotlin AST. I was talking a lot about AST, but let's talk a little bit more about what is actually under the hood and what is actually Kotlin AST. When we decided to rethink the Kotlin Analyzer, there were a couple of different variants what we can use. The first obvious variant is Program Structure Interface, PSI. I think you heard about it if you ever implemented any support of the language in IntelliJ. It's actually an interface coming from IntelliJ, pretty nice, and we were already kind of using it when transforming our Kotlin syntax tree into our universal tree. Another possible solution could be front-end intermediate representation. 2 years ago, that was something new. We saw that looks nice, that looks similar to what we have in our Java analyzer, and we thought maybe we can use this one. We tried it a little bit. It worked on some simple examples. There were a lot of exceptions on some not simple examples, and that's better API. That's something that we really wanted. There was one tiny problem that was not ready for production, so we could not rely on this. And another third possible solution was a unified AST. This is actually a representation of AST that is similar for Java and Kotlin, used in Android Lint. There is another problem, because it's the same for Java and Kotlin, the precision is low. So if you want to have some rules about the syntax, we could not rely on this. So it was easy to have some table to compare the stuff, and the obvious winner was PSI. So we decided to go for PSI. But that was not that easy, because there's something wrong with PSI. The first problem is nullability hell. What it is? When we are writing some analysis rules, and for example, we want to visit T-binary tree, in our case, if binary tree was not parsed, we could never actually reach the check, because that's how our analyzer works. But the problem is, when we are relying on PSI, it's all nullable. And what can we do? One of the possible solutions is just using safe calls. And if it's just 2 of them, that's OK. But if you have nesting like 5, 7, 10 levels of nesting, looks kind of ugly. And we didn't want to use that approach, and maybe we can write it better. Another possible solution was to use Elvis operator and return. There was another problem. That's coverage. Not actually the coverage that we want to please the tool. It's more about that we're introducing actually unreachable paths in our code, because we know that it's never going to be null, but we still introduce another path, And maybe that's something that we want to avoid, so we wanted to use something else. Another solution is to use non-null assertion. Why not? Nice coincidence, yeah? Every time I put non-null assertion, something like this happened inside me, and like, don't do it, please, don't do it. Okay, and after a lot of considerations and discussions in our team, we decided, okay, let's use non-null assertion with one tiny improvement. Let's always add a comment with what was the assumption. And in a few slides, you'll see how it helped us. So that's how we work now. So if we see that something is nullable, but we are definitely sure that it's never going to be null, we can use a null assertion, but we always put a comment why. So that's one problem that we kind of solved. Another problem is lack of documentation and naming. There are some JetBrains guys, I guess, here. Sorry for that. But yeah, what is KT named function, guys? Again, calls. Any idea? So we are people who like have, some computer science degree, and we can reason about things. We thought like named function is a function with a name. It's obvious, yeah? So when we implemented a bent function name rule, we said like, okay, name is nullable for some reason because it's compiler and like everything is nullable in IDE. So let's just say non-null assertion and named function always have name because that's obvious. And a couple of days later, we tested this rule on this example. Know what it is? This is an anonymous function. They're like, but it's anonymous function. It's anonymous, it doesn't have a name, so it shouldn't be KT name function, and we never go there. So you know what happened. We received null pointer exception. Where? Exactly here. So after much of an investigation, talks to brains guys, we realized that KT named function is not about the function name. That function was named with keyword fun. Like, take a minute and reflect on it. So yeah, and that's not the only gem like this in the compiler, so there are a lot of stuff like this, and we have to deal with it somehow. Another fun part was compiler diagnostics. Sometimes we are using compiler diagnostics because like compiler already did the work for us. Why shouldn't we just reuse it? And for deprecated code usage check, we actually reused compiler warning. It looked like this. So we used the KT element provided by compiler. And then one time, one user reported an issue with deprecated enum that looked like this, and said that I have index out of bounds exception here when I analyze my code with this. That looked very non-obvious why it could happen there, but we had to investigate, find out what's the problem. So why index out of bounds exception happens? Because in our tools, we try to report an issue on something that is out of range. Why? After some investigation, we find out that it's actually here between entry 1 and the opening parenthesis. Why? Because when you put a deprecate on, in Kotlin, it's also a primary constructor, you actually deprecated a primary constructor. And when inside you have entry, you are actually also calling primary constructor without naming primary constructor. So the deprecated part was also a primary constructor, but there was no representation in source code. But compiler still said us that this element is has a warning on it. So after looking at the IntelliJ, how IntelliJ handles this, we find out that IntelliJ just highlights the opening parenthesis, and we did the same. And so now we know that in program structure interface, there are some elements that doesn't actually exist in the source code. That was nice to know. Knowing all of this, we thought that maybe eventually, when theory is ready, we can use this one. So we have a lot of hopes for K2, guys. No pressure. So Actually, Sonar Kotlin 2.0 was released. It happened like in 21st of June, 2021. And what it actually had. We improved the precision of existing rules because we rewrote them on our new engine. We added a few more rules with semantics. We added semantic, and we also updated the mappings with the rules with detect, Android lint, and edit KT lint. So we expected the feedback would be like this. Our users will be extremely happy because finally we are doing what they want from us. We are supporting Kotlin, improving the precision. And the feedback was kind of like this. Why? Because I think the day when we released, or the next day, our community forum looked like this. Kotlin Sonar Analyzer is taking too long, it's too slow, we have out of memory, it's taking forever, it never ends, and it was painful because, like, of course we tested our analyzer, of course we tried different projects, and we never faced this problem. And what we usually do in this situation, we gather a meeting. We all gather a meeting to discuss what we're going to do. There were some managers, there were developers, and said, like, we have a performance problem, let's do something. There was one idea, maybe we should introduce caching, or maybe we should do some parallelization there. There was one guy who said, like, maybe let's find a bottleneck and fix it. We threw him out of the window, of course. But then we decided, okay, maybe let's find the bottleneck and fix it. And one of the candidates of the bottleneck was actually this rule, commented out code rule. What is this? In Sonar, we have a rule that if you comment your code, we say, please don't do it because it's a bad practice. How it actually worked? We go through all the comments, and if we say that this comment is code, we highlight it as an like code smell. If we assume that we see that it's just a normal comment, we say, okay, let it be. So before 2.0, it worked perfectly. Like, everybody was pretty happy with this. Why? Because we took every comment, we parsed it, it was pretty cheap, and then if its parsing was successful, we reported an issue, and if it was not successful, we assume it's not a code, and we do not do nothing. And here is one funny example. Is it a code? From Kotlin parser, without no semantic, it's actually a code, because world could be an infix function. And basically all 3 or more words in Kotlin are considered code. In order to overcome this, we had to have some ugly workaround. And once we added semantic model into our engine, we decided, okay, let's just rewrite this, and it should be better. So after 2.0, instead of just parsing, we introduced parsing and generating semantic model. And with semantic model, we can definitely distinguish whether it's code or no. But that was one tiny little problem. It was slow, like very slow, like extremely slow. And there are a lot more problems with semantic model. So first of all, there are compiler bugs, because now we are trying to compile and generate semantic model for all the comments that you have in your source code. And we stepped into a few compiler bugs because we are like compiling the things that should not be compiled. Then could be code with mistakes, and your code with mistakes could still be a code, and we should report an issue. But because there was a mistake, we'll have some false negative in our rule. Then code might not be written in Kotlin. Still would be nice maybe to report it, but our current approach doesn't have it. And like the biggest problem, it was extremely slow, because generating semantic model is a very expensive operation, and doing it like thousands or hundreds of thousands of times takes time. So we needed some immediate solution, and we are not proud of this, but we decided to comment out our commented out code rule. And imagine what? For a year, there were 0 complaints. Like a year, it was like this in production, and nobody cared. Then I got back from my maternity leave, started talking about this at the conferences, and people started reporting. So several months later, we had 1 complaint, and we said, like, okay, maybe we have to fix it. And yeah, we fixed this. So now instead of parsing or compiling your comments, we introduced the heuristic algorithm. So it's like probabilistic, and we try to answer the question whether what you wrote in the comment looks like code. So we had some potential structures. We are checking if there is for, if, catch, or something. And then if the calculated probability of this being a code is high enough, then we parse. And if parse was successful, we say that, okay, it's code. If it was not successful, it's not code, so that's okay. I know that's a probabilistic algorithm, so of course it can have false positives, false negatives. So far, we had no complaints, but feel free if you are able to trick it, report it in our community. And yeah. Okay, now you know some basic stuff about how we can implement some rules, how static analysis works. So let's just for fun implement some simple rule. So what the most simple stupid rule I have in our head, it was like unused import rule. So unused import rule, how we actually can implement this. So we decided maybe that's okay just to collect all potential references, group them by importable name, filter out everything that's referenced in kdoc, filter out everything that's referenced in the code, and then all the remaining imports could be considered unused. Sounds like smart. Sounds like that's how we should implement this. And then we forgot about companion object. A few days later, we discovered this example that is a false positive. And why we forgot about this? Because basically, you can definitely see that you are using my class.myConstant. This is a constant from this class. But the problem is that actual importable name is .companion. You don't write it, but when you're going to compiler, in the Kotlin compiler and trying to find it from semantic model, it returns .companion. It's not what you have in your imports, and that's why there is a mismatch and we report a false positive. Okay, so we can fix it. And then we forgot about named companion object. Because people sometimes do named companion objects. And actually, then it would be not .companion, but it would be .named. And after finding some investigation, remembering that Kotlin compiler API is very well documented, we find out this magic function that we can actually check that something is companion object. So, okay, we overcame companion object, and then we got another problem, unresolved imports. Sometimes in static analysis there is a situation where you don't have like binaries or libraries because people forgot to provide them, and without this we cannot generate properly semantic model. And because like my class was not found, we could not find it in references, and then we report it as unused. Of course, we should not do it because we don't want to report the false positives. So we tried to filter out every import that has errors. So now we see that if there is any error in type resolution, we tried not to report you anything. So it could be some false negatives, but that's just a compromise. Okay, we thought that's it, but no. Another problem came from delegates. So you know in Kotlin you can actually implement some local variables, or you can have fields, delegates. And here you can see that you import get value, but you never reference get value because you just have by. And implicitly you're using get value. And of course our current algorithm was not supporting this, so we have to figure it out after working a bit closer to Kotlin compiler and investigating how it's resolved and where it's resolved. We figure it out. So what we actually do, if there is no semantic model, we just skip all these imports that are connected to delegates. But if no, we can get importable name from Kotlin compiler with some tricks, and then we can actually understand that this by delegate is actually using operators.getValue and filter it out. Another pain point was operators overloading. And you know, it's just one single rule, one stupid, simple, unused import rule. So you know, in Kotlin, you can overload a couple of operators. Thank God it's not Scala where you can overload everything, but still. You can use like in, not in, or invoke, but in your import it would be just contains, invoke, plus, minus, so it won't be just an operator sign. This is the problem, because when what you see in your AST is not actually what you import. And what? This is actually how it looks in operators. And of course, we reported false positives. How can we fix it? Actually, again, we can try to dig more into compiler, into semantic model, find out the importable name, and somehow map this in or not in, or into contains. And this is how we filter out contains, plus, and assign operators and all other overloaded operators. But there is still a problem with invoke. What's the problem with invoke? From your point of view, from Kotlin AST point of view, there is no difference whether you call a function or whether it's just an overloaded invoke operator. So there is no way how you can distinguish it without just visiting all call expressions. And that could be costly because, you know, in a single file there could be a lot of call expressions. That's why we introduce some sort of a laziness here, and we try to only do this if there is at least one invoke import. But if there is at least one invoke import, we had to go through all the calls and find out if there are actually invokes or no. So, okay. Do you think that's it with unused import? Of course, no. Incomplete semantics. A few slides ago, I told you that there could be a situation when some binaries, libraries are missing, and we don't have semantic, there are errors. There is a little bit like different situation connected to this. Sometimes something is missing, but because compiler is smart, it can resolve what you have to something different. So, for example, you have imported like do something function, and you are using this function. And this is the function in package A. And in some external library, there is also a function with the same name. Maybe a little bit different signature, but still the same name. And for example, our client decided to trick a little bit with our properties and decided not to pass binaries there. So libraries are present, but your own binaries are not. Then, when we are analyzing this, you see that package a.something is unused, while it's definitely used. Why? Because this do something was resolved to a different import. So instead of having like error in the imports, we don't have any imports of being unresolved, because it was actually resolved, but to something different, and we still have false positive. And the sad part that we can do nothing with this. So we can try to trick as much as possible to minimize the amount of false positives. We can try to understand if there are some errors. But if everything was correct and just resolved to something different, we have no way to distinguish this. So please, if you're using Sonar, don't trick your properties. Don't put any stupid value into Sonar Java binaries or Sonar Java libraries if you don't know what they're doing, because then the result could be unexpected. And do you think that's it? Okay, no. In Java 16, do you know what happened in Java 16? I'll tell you. Some time ago, we received another funny false positive. It was coming that import of Kotlin stream to list is unused. And then you see in code and you see like, no, it's definitely used. Like, what's the problem? Actually, since Kotlin 1.2, there is a function, extension function on stream to list. Because like, why not? We all want this, and that's how we work with streams in Kotlin. And then, in Java 16, there is function to list on stream, which is default function. And if you know a little bit how JVM works, Java works, and you know that your own functions, instance functions, have higher priority than extension functions, and those one will be resolved. So what's the problem with actual example? This user was running his code on Java higher than 16, so probably 16 or 17, but targeted Java 11. So basically in the API, the list function is not present, but it was somehow present in the, present in your environment. And because our analyzer did not distinguish this, whether it's targeting Java 11 or it's targeting your Java version, we resolved it to list function from the string instead of to list function from Kotlin. And good news that we know how to fix it. We know that there is a problem, and we are going to fix it very soon. But currently, yeah, that's what we have, so sorry. So, of course, that's not it with unused import, but we are limited in time, so I cannot tell you all the stories that we faced, all the false positives and funny facts about compiler. But what I wanted to tell you, writing static analysis for any language, and especially for Kotlin language, is all syntax sugar, all the features. It's like never-ending story of balancing between false positives, false negatives, and proper precision. So it's a lot of fun, sometimes pain, but still a lot of fun. So let's talk a little bit about achievements, what we actually achieved after releasing Sonar Kotlin 2.0. We improved precision because we added semantic. We had 108 rules, and actually now when I'm presenting at KotlinConf, my teammates released another version of Sonar Kotlin. So currently we should have around 120 rules or 100 like this. So it's even more. We already had 13 releases, and 14th was, I guess, just done yesterday or today. We have rules for regular expressions. We have rules for security, Android security. We have up-to-date external linters mapping. So integration with detect, Android lint, and KT-lint should be is done properly now. And what's the most important, we have fast community handling. So every time you report any issue, face any false positive, we try to react fast and try to fix it fast. And a few takeaways that I want you to take from this presentation. First of all, Sonar supports Kotlin. So if you need some static analysis tool or you're using Sonar but don't use Kotlin, so you can consider this. Another part that static analysis for Kotlin is fun. Sometimes pain, but most of the cases fun, and you learn much more about the language. And please be active community members. A lot of things that I showed you today were discovered because of our community. So we could not test all the possible variants of code base, but you can. So if you report us issue, we'll try to fix it and become better and improve and won't face this issue next time. And another important thing that if your current approach is not satisfying your needs, that's what happened with us in the beginning of my talk, don't be afraid of just throwing it away and rewriting it. And you'll see JetBrains guys are doing the same with K2. And a few special thanks. First of all, there are two people who actually made this Kotlin Analyzer 2.0 possible. They're both here at KotlinConf. So, and without them, I wouldn't be there. Without them, there would be no Sonar Kotlin 2.0 and no Sonar Kotlin 2.14. And now Sonar Kotlin is actually under the umbrella of JVM Squad. So the same team that works on Sonar Java is actually working on Sonar Kotlin too. And thank you for being here. Thank you for listening to my talk. And if you have any questions.
You talked earlier about cross-language ASTs and the like, and one thing that I didn't hear in your presentation, I'm not actually certain, is suggested fixes and outputting changes to source code to fix the bugs out of Sonar's scope, or is something that you just didn't bring up in your presentation, or?
You mean like the rules are just implemented in Sonar, or?
I mean, so it's clear Sonar reports errors. Does it suggest changes to the source code that would fix those errors?
Okay, sometimes in the error messages, we are actually trying to say like not just this is a problem, but try to like replace this with that or delete this. And there are a couple of rules that have quick fixes in IntelliJ, like on in other IDEs. But for Kotlin, we don't have quick fixes yet. It's available for Java, C++, I guess Python, but for Kotlin, it's in our roadmap, but not yet there.
Hi. Thank you very much for mentioning the integration with Detect and other tools. I'm actually the maintainer of Detect, and I have one question. We do have our first-party plugin, like maintained by Detect maintainers, which is called Sonar Kotlin, which is also super confusing now as a name. But it's under like github.com/detect/Sonar Kotlin. I'm wondering if we can like deprecate it now and say like, don't use that anymore, refer to Sonar first-party integration with our tool, because for us, it's like we are maintaining integrations with a lot of other tools and frameworks, and yeah, we don't use Sonar, so like there is like a discrepancy between us maintaining this tool and knowing how the integration works. So yeah, I would like to hear from you.
I think we can talk after the presentation because it still depends on what it is doing. If it's just to have mappings up to date, I think you can deprecate it. If it's doing something more, maybe let's discuss it. I'm afraid to like answer right now without like having much more information. But thanks for maintaining this.
Hi, great talk. I wonder if you will have the same problems you had with the input rule if you use FIR, because I assume that is a better representation for analysis. Is it the sugar representation?
I hope that we'll have like better, but I don't know exactly because that's all the problems are not actually in the IST. The problems are coming from semantic model. Now semantic model is a binding context that we are using, and there are a lot of things that are not clear, not well documented, and that's hard to find out of them. And as far as I talked with compiler engineers of K2, they promised that there would be a nicer API. So maybe all these problems with semantic would be solved, but I don't know yet because it's still not ready for production. Any other questions? I'm curious, nobody's asking about multi-platform.
So yes, the question you wanted, does it support multi-platform, or when will it support multi-platform?
Actually, I think it's one of the most voted feature that, unfortunately, currently, if you're using multi-platform plugins, Sonar doesn't find, Gradle scanner for Sonar doesn't find any files. So you can use just Sonar scanner, but it's a little bit more work. The good news that once we are back from Kotlin Conf, I think in May or June, we plan to start working on this. So maybe by the end of the year, we'll have the support of multi-platform.
And I have a great library to test it.
Sure, thanks.
Yep, thank you for the talk. And one more question: do you plan to do some heavy analysis calculations, like interprocedural analysis, or using bytecode? Because as I understood, you're relying on the fact that your code is compiling, so you can do more interesting checks and use more information at once, all the libraries, dependencies, and so on. Yeah,
currently we that's how we work. We rely on the compiled code, and without this, we cannot generate semantic model. And I think for now, we will continue working like this. Maybe somewhere in the future, we'll consider another process, but you should also understand that it's the same team that is working on Java Analyzer is working on Kotlin. So basically, if we'll have some innovation, it will first appear in Java, and maybe we'll like naturally come up with it in Kotlin.
Yeah, and and the question is, do you plan like do some interprocedural analysis, like for example, virtualization, like or trying to understand if those variables are recursive and you can't initialize them, because right now it's impossible to do this in the Kotlin compiler because you have to do like local analysis, but maybe you can do this.
Yeah, that's a good question. I think for now, no. So it's definitely something that we dream of. We have plans like, of course, we want to conquer all the world and like implement all the possible rules that we can. We have limited resources, so maybe sometime in the future, yes, but for now, probably no.
Yeah, thank you. Because this is something that you can do definitely better than the Kotlin compiler, because Kotlin compiler will never do this non-local analysis.
Yeah, makes sense. Thanks for ideas. Yeah.
Yeah, I think we're out of time, so if you can just ask questions directly. Thank you so much.